Hello, today we continue studying thermal phenomena using the example of phase transitions, and we'll look at another question. An aluminium cylinder with a mass of 155 grams was cooled in liquid nitrogen to a temperature of minus 196 degrees Celsius. Then the cylinder is immediately placed into an insulated container containing 80 grams of water at 15 degrees Celsius. What will be the final temperature of this system? If your answer is 0 degrees Celsius, determine the mass of water that has frozen. So the data is already written out here, and we've immediately converted it to the International System of Units. Therefore, the mass of the aluminium cylinder is 0.155 kilograms, and the mass of the water is 0.08 kilograms. Note that the temperature here really does correspond to the temperature of liquid nitrogen, minus 196 degrees Celsius, which is extremely low. Now, we need to figure out what will happen if this cooled aluminium cylinder is placed in water at 15 degrees Celsius. What will ultimately happen in this system? Well, to start, let's schematically show roughly what stage the water and the aluminium cylinder are at. Because when we visually show that there is a substance at a positive temperature, in this case we have water here, and somewhere over here at minus 196 degrees is the aluminium cylinder. So the task now is, of course, that due to this temperature difference, these bodies will try to reach thermal equilibrium. That is, the cylinder will heat up and the water will cool down, and we need to understand what this will ultimately lead to. Naturally, first and foremost, we should focus on the water, because we realize that when it comes into contact with such a cold object, it is quite possible that it will freeze, and so we need to consider the point corresponding to its melting temperature, which is 0 degrees Celsius. And the cylinder, of course, will also most likely tend towards this temperature, but whether it will actually reach it or not is something we need to determine. So let's first calculate how much energy the water can release as it cools down to 0 degrees Celsius while still remaining in a liquid state. How much energy the ice needs to warm up to 0 degrees Celsius, we'll compare these two values and see what that leads to. So let's look at the first amount of heat, which we'll denote as Q1. This amount of heat is determined by the formula C, M, and the change in temperature. In this case, the change in temperature is T0 minus the temperature of the water, which is T2. Pay close attention to the indices. And here as well, we must be sure to use the correct indices for water. That is, this is C2 and mass 2. We've entered all the data, so let's calculate the numerical value of the energy obtained. So 4,184 multiplied by 0.08 and by the change in temperature, which is 0 degrees Celsius minus 15 degrees Celsius. As we can see, the heat here will be negative, naturally, because the water is losing it. So after performing the calculation, we get a value of minus 5,020.8 joules of energy, which is the result we have obtained. That is, this is exactly how much energy the water will lose as it cools down to 0 degrees Celsius. And now let's calculate how much energy the aluminium needs in order to heat up to 0 degrees Celsius. Here, the formula for heating will be exactly the same, only we use the index for aluminium and the temperature difference T0 minus T1. Let's substitute the values. So the specific heat capacity of aluminium according to the conditions is 653 and the mass of aluminium is 0.155, and here we get the temperature difference, 0 minus 196. In this particular case, the two negatives, as you may recall from basic mathematics, make a positive, and so the value for the amount of heat will be positive, which is quite logical. The aluminium cylinder is receiving heat. This makes sense because when you subtract a negative number, it is equivalent to adding the absolute value of that number. And so the value we get for this amount of heat after performing the calculation is 19,802.8. This positive value indicates that heat is being absorbed by the aluminium cylinder, which aligns with our expectations in this scenario. So that's roughly how much energy this aluminium receives, or needs to receive, in order to be heated up to 0 degrees Celsius. Now let's compare these two values. That is, the aluminium needs to receive about 20,000 joules to heat up to 0 degrees Celsius, and the water can give off about 5,000 joules when cooling down to 0. What does this tell us? It tells us that water, while in its liquid state, is not able to heat the aluminium up to 0 degrees Celsius. And when it gives off those 5,000 joules, that is, when it cools down to 0 degrees Celsius, the aluminium will still be somewhere in this range, meaning it will still be at a sub-zero temperature. Therefore, the only thing left for the water to do is to continue giving off heat, because it is at a higher temperature than the aluminium, and as a result, it will start to freeze. So it turns out that the process of this water freezing will generate heat, which will then be used to further heat the remaining aluminium up to some temperature. Therefore, we need to determine whether there is enough water, and specifically enough energy released during its freezing, to heat the aluminium up to the final 0 degrees Celsius. In other words, we need to find out how much heat the freezing water can actually generate. How do we calculate this? To begin with, we can simply calculate the mass, which we'll denote as M3, that is, how much water needs to freeze in order to generate the required amount of energy. And how much energy needs to be generated? In this case, it's the difference between how much energy the aluminium needs to receive and how much it actually received from the water. I take this amount of heat as an absolute value because we're taking the pure difference between these energies, so as not to take into account the signs associated with these amounts of heat and to avoid any confusion later on. And then the amount of heat we've obtained should be divided, according to the formula, by the specific latent heat of fusion, in this case freezing, for the given water. So let's calculate an approximate value. So in this calculation, we first take the value of 19,800 and then we multiply that number by 2.8. After that, we subtract the result of 5,000 multiplied by 20.8. This entire expression, the result of the subtraction, is then divided by the specific latent heat of fusion, which in this particular case is a value equal to 334,000 joules per kilogram. After carefully performing all of these calculations step by step, we arrive at an approximate value which is about 0.0442 kilograms. If we want to express this mass in grams instead of kilograms, we simply multiply by 1,000 and that gives us a value of approximately 44.2 grams. This is the final answer after all the necessary mathematical operations have been completed. In other words, we're saying it's 44. 2 grams of water need to freeze in order to provide the remaining heat so that the aluminium can be heated up to 0 degrees Celsius. Now let's turn to our data, specifically to how much water we had initially. We can see that there were 80 grams of water. This means that out of those 80 grams, 44.2 grams are frozen. Accordingly, the remainder will stay in a liquid state. And the temperature of the entire system ends up being 0 degrees Celsius. Because this amount of water was enough for the ice to eventually be heated up to 0 degrees Celsius. Thus, the system will contain ice, water and the aluminium cylinder all at 0 degrees Celsius. At the same time, there will be 44.2 grams of ice in the system. And as for the remainder, in those 80 grams, you can calculate this yourself, it will be in a liquid state. This is the way we can reason when solving such problems. By examining the sequence of thermal processes and calculating them based on known formulas. That concludes our lesson. See you in our next videos. Goodbye to everyone.